Now that we've had a chance to discuss what the Lagrange error and the alternating series error bound is, I want to just do a couple of quick practice problems just for us to get a sense of how we might find the Lagrange error and compare it to the quote unquote actual error for some of these problems. So let's take a look at this first problem. It asks us to approximate the error using either the alternating series error bound, if it's applicable, and the Lagrange error bound. So let's start with looking at the fourth degree Maclaurin polynomial to approximate the 10th root of e. So the first thing I'm going to do is I'm going to approximate what the 10th root of e is. And it's important to make sure we understand what the function is that is being described here. If it's the 10th root of e, we're saying that our function f of x is equal to e to the x. And what we're trying to do is approximate what the function is evaluated at 1 over 10. That would be e to the 1/10th power. So that's the exact value. We're trying to approximate it using a fourth degree Maclaurin polynomial. So let's go ahead and let's write that out. So we've got the fourth degree Maclaurin polynomial. Since we know our function is e to the x, we can use our elementary series and evaluate that elementary series at 1 over 10. And what that would look like would be 1 plus 1 over 10 plus 1 over 10 to the second power all over 2 factorial plus 1 over 10 to the third over 3 factorial. And since it's a fourth degree, I'm going to stop at the fourth degree. There it is over 4 factorial. Now, for the sake of time, I'm just going to give you the approximation here, but I would encourage you to pause and try to calculate this on your own using your calculator. Just make sure you get the same thing I do. And oops, I'm going to just go ahead and write that out. It's 1.051708.3. I'm going to stop there. I think that's enough decimal places to give it a good sense of what our approximation is. Now that we have our approximation, we could find our exact error, or quote unquote, I should say actual error, if we were to subtract e to the 1/10th minus this approximation. But we're going to pretend for a moment we don't know what e to the 1/10th is. We're trying to approximate it using a Maclaurin polynomial, and we're trying to use our error to find out how close our approximation is. Now, if we look at our series here, we'll notice that this is not an alternating series. So we can't use the alternating series error bound. So instead, let's use the Lagrange error bound. And let me just write this in a separate color so we know what we're starting to build. So we would say that our Lagrange error also can be written as the remainder of after the first 4 terms evaluated at 1/10. And we know that this Lagrange error is going to be less than or equal to the following. And if we review the structure, it's the maximum value of the n plus 1 order derivative evaluated at z, at some value z. Again, if you're not sure what z is, watch my previous video on this, times x minus c to the n plus 1 power, all of this over n plus 1 factorial. And since we're looking at just the error, we're just going to go ahead and write the absolute value of this, right? Whether or not it's positive or negative, whether or not it's an overestimate or underestimate, I'm just concerned about finding the error or the distance here. Now, let's start plugging in a couple things that we know. First off, since we're evaluating this function at 1 over 10, that's my x value. So I'm going to write that in. That's 1 over 10. And since this is a Maclaurin series or a Maclaurin polynomial, it is centered at 0. So I'm going to go ahead and write that. We use a fourth degree Maclaurin polynomial. So the next term, n plus 1 term, this would have to be the fifth term. So I'm going to write that. And same deal over here. Down here, we're going to write that this is 5 factorial. So the only issue now is for us to find out what the highest possible or the largest possible value of the n plus 1 order derivative evaluated at z is. That's our goal. And just to be short, we call this m. And again, we're not too concerned with trying to find that z value. Remember, we have some z value that's in between x and c. C here being equal to 0, x here being equal to 1 over 10, we're saying that there is some z value in here that's going to create the largest possible order derivative. Now, again, we're not worried about finding z, so let's think about this. What's really nice about the e to the x function is that every order derivative for e to the x is simply e to the x. So what m is going to be the largest possible value for the fifth or I should say, the fifth order derivative is e to the x, is the largest possible value that e to the 1 over 10 could give us. So you would think, oh, well then, yeah, z would just be at 1 over 10. But this is kind of a silly proposition here because, again, if we knew what e to the 1/10 was, then there would be no reason for us to actually be doing this problem. There'd be no reason for us to want to approximate something that we know the exact value to. So although you could use 1/10 here, or e to the 1/10 as your m value, again, if you really think about it, it's kind of silly for us to do so. Pragmatically speaking, the whole purpose of this is to try to come up with an m value that we know is going to overestimate or give us the largest possible error within a reasonable extent. So this is where we just kind of use some number sense. And I say, all right, well, e to the 0 power I know is equal to 1, and e to the 1 power is approximately 2.718, or the value of e. So if I'm trying to give an overestimate for e to the 1/10, it probably makes sense to use a number that's closer to 1 than it is to 2.718, right? So here, this is where we might see a couple of different values that students might use. If we want to be really safe, we might want to use something like 1.5. I would say don't be too conservative here. Don't try to get it too close to the actual value of e to the 1/10. That doesn't really make sense for us to labor over that. So instead, I'm just going to use something closer to 1.2. So I'm just going to go ahead and write 5 over 4 here, right? I know that e to the 1/10 is probably going to be less than that, but again, I'm just trying to overshoot my bounds here. So using that value for m, again, I did not stress about what the actual value of z was. I wasn't trying to get it as close to 1 over 10 as possible. I was trying to create an overestimate for what the highest order derivative value at 1/10 would be for this function e to the x. And I just use 5 over 4. So here, now that I have 5 over 4, I'm just going to approximate 5/4 times 1/10 to the 5th power, all divided by 5 factorial. And that comes out to approximately, let me just go ahead and put that into my calculator, times 0.1 raised to the 5th power, all of that divided by 5 factorial, or the same thing as all of that divided by 120, should give us 0.00000, how many zeros is that? 0, 1, or 1 times 10 to the negative 7th power. So the Lagrange error there, even if it's representing the worst possible error there, is actually a really good approximation. We're seeing that this approximation that we came up with using our Maclaurin polynomial, our 4th degree Maclaurin polynomial, we're saying that it's going to be accurate by a value that's no worse than 7 decimal places. So that's pretty darn good. And if you have the time, go ahead and find the actual error by taking e to the 1/10 power and subtracting our approximation from it, and you'll see that that error is even smaller, and it's supposed to be. We're coming up with the worst possible error here for the Lagrange series error bound. All right, or the Lagrange error bound, I should say. Let me do one more problem with you, this time now circling back to using a trig function. So let's go ahead and try number 2, part A. And we're going to use a 5th degree Maclaurin polynomial to approximate sine of 1. So a 5th degree Maclaurin polynomial approximate at 1. So again, I'm going to use my elementary series to write this out. And I'm just going to plug in 1 for all of my x's, which is 1 minus 1 over 3 factorial plus 1 over 5 factorial. And if you don't have your elementary series memorized, what are you waiting for? Get those memorized. So when I calculate this, this comes out to approximately 0.8416 repeating. And while I'm at it, let's just go ahead and let's compare it to what the sine of 1 actually is. The sine of 1, this is actually approximately, if you make sure in your radians, 0.84147. So we see that our Maclaurin polynomial right away is pretty good. But let's go ahead and let's find their unique errors. The first thing I'll notice is that the way the series is written right now, this is an alternating series, right? So I can actually use the alternating series error bound here, which now that we've worked with the Lagrange error bound a little bit, we realize just how easy this is. We know that this has got to be less than or equal to the absolute value of the next unused term. So what would be the next unused term in this series? It would be -1 over 7 factorial, right? The next term would be negative over 7 factorial. And this comes out to 0.00001984. That's a pretty good approximate. That's a pretty good error, right? It's a pretty small value there. Now let's compare that to the Lagrange error, because we can always find the Lagrange error for any approximation. We can't always do the alternating series error bound, but we can always do the Lagrange error bound. And we know that this is going to be, again, less than or equal to the absolute value of, and hopefully you know the structure a little bit better by now. Since this was a 5th degree Maclaurin polynomial, I want to do x minus c raised to the 6th power. It's the next unused term, raised to the 6th power. So this would be raised to the 6th power over 6 factorial. We know inside the parentheses, it's x minus c. Well, we're evaluating 1, so x is equal to 1, and c is equal to 0 because it's a Maclaurin polynomial. So I'm just going to write 1 here inside the parentheses. Now, as for this magic m value, we are concerned with asking ourselves, what is the highest order, or what is the largest value that could come out of the 6th degree term, 6th derivative evaluated at some z? And again, we're not stressed out about finding that z value. And we already know from our previous lesson that the largest value that could come out of any derivative for sine or cosine is always going to be equal to 1, right? That's just the range of that function. So we can just easily put in 1 there. And when we punch that in, we get approximately 0.00138. Now, if we had just looked at this Lagrange error isolated, we would say, hey, that's pretty darn good. That's close to accuracy to 3 decimal places here. But we see that our alternating series error was better, and our actual error, the difference between what we found using our Maclaurin and our by evaluating just sine of 1, was even smaller than that. So hopefully this gives you a sense of comparing the 3 different errors, the actual error, just whatever your remainder would be if you somehow knew how to find the exact value of that function, the alternating series error, because it happens to apply here, and the Lagrange error bound, which will always apply, and it's always going to represent the worst possible error.